Yesterday we started the this very important topic on what you should view this. You should view this as yet another type of probability calculation or calculation using a PDF and PMF, isn't it? And basically, so given some random variable with some PDF or PMF, doesn't matter, we are doing, let me write out the most general thing. The E of G of X, for it turns out, right, this is the kind of a most general formula we can write, assuming for continuous G. So for G of X being a purely continuous random variable, right? X is a special case of G of X, clearly, right? And this and the summation I don't want to repeat. So this is basically referred to as the law of the unconscious statistician. I hope some of you went and Googled that phrase and a whole page on it. So I've been doing it for 30 years, and I don't know, I stumbled on this term only in the last few years. Before that I wasn't myself aware of it. Earlier we used to call it the fundamental theorem of expectations, but this sounds a lot nicer. So anyway, so the condition of course is that, right, that is E of G of X exists, the existence of this integral if and only if E of mod G of X is less than, right, exists or is less than infinity. Right, this is just to ensure, as I said yesterday, you don't write infinity minus infinity as some finite value. Okay. So where do we go from here? Yeah, so we so examples, of course, E of X itself, and then E of X squared, and so on. These are the important individual applications of G, and we will do many more. The dot really means that there are more instances of E coming our way. But for now, if we focus on E of X and E of X squared for particular PDFs, for particular distributions, we get, I'm not going to do do a big calculation on the board, but just one or two I just do for illustration purposes. So let me start it up here. Okay, keep this blank. Right, these are examples again of specific PMFs, PDFs. Right. We start with a discrete. The simplest is Bernoulli. So it turns out for this very simple case, which is what, just 0, 1, and probability of X being equal to 1 being P. So what is the E of X? It's very simple, it's just 0 into 1 minus P plus 1 into P. That's all, just following the definition. This is basically P. What about E of X squared? If you apply just simply this lotus. Turns out that X squared and also takes values only 0 and 1, so it's very easy. So again, it's exactly the same thing. 0 squared is 0 and 1 squared is 1. So you get, once again you get back exactly the same number. This is the very unique thing about this Bernoulli distribution, that for which E of X equals E of X squared. Right? Okay. So yesterday I also pointed out that E of X squared is always non-negative. Right? There is no way that E of X squared can be negative, and that is a general theorem relating to the the average of some non-negative function, not necessarily just X squared. If you tried X power 4 also, you will get the same result. Okay. So then the discrete uniform, I just want to mention that although I am not going to calculate E of x squared because it is a little more involved, but E of x can be straight away written down. So what is a discrete uniform? So this is a new notation we are using. So if I say discrete uniform n, it means it's like a die roll from 1 to 6, except that I am taking 1 to n instead of 1 to 6. What is going to be the E of x for this? It is always n plus 1 by 2, which is how we got the 3.5 yesterday for the case of n equal to 6. This just this one thing is worth remembering, right? Not n plus half, but n plus 1, right? N plus 1 by 2. This is again very easy to derive. All you have to do is do that arithmetic, sum of first n natural numbers is n into n plus 1 by 2. If you know that, if you do that, then it's immediate. Okay, let's move on to the most somewhat more theoretically interesting things. What if I had an indicator random variable, right, which is basically nothing but Bernoulli? Suppose IA is indicator of A, of some event A with probability PA, let's say, is equal to P. This ties into the Bernoulli. So you can say, well, definitely, what is E of IA going to be? Just going to be equal to P itself. But normally we don't think of when we don't we want somehow, I mean, I may have given the impression yesterday, for example, that probabilities and expectations are, expectation is something built on top of a PDF, but you can think of probability itself as some special case of an expectation, right? The idea of expectation actually, what does it do? It enlarges our concept of probability, right? Every probability can be viewed as an expectation. That is what this is saying. So in other words, the probability of an event is actually itself an expected value. So that these two are, right, very maybe I should have put this ahead of this, but anyway, it does not matter. Okay, so okay, so then let us go on to some other discrete binomial, let us say. Now for other PMFs, it turns out that the actual calculation, if you want to do, is a little non-trivial. So basically it means that you have to do a sum of this kind, k times n choose k p power k 1 minus p power n minus k. There are several binomial, sorry, this should be binomial, let us say n small n comma p itself. So E of x equals this. Where did this k come from? This is this value taken by x. Okay. So if you did not have this k, you would just be summing all the probabilities for the PMF and it will be equal to 1. With this k, what happens? What do you think the answer is? It is n times small n times p, n p. How do I get that? There are several ways of getting it. One is to, as we will see, we can extend the concept of or we can exploit the concept of the binomial being a sum of IID Bernoullis and get that NP, or for now, since we are not that far into expectation, just apply from first principles we apply the summation. All you have to do is cancel this, write this, what is it, k into n choose k is what? K into n choose k is basically k times n factorial by k factorial to n minus k factorial. So this k will cancel this k minus 1 factorial and give you k minus 1 factorial, but then the summation will have to go from 1 to n, not 0 to n, because you have, right, if you go from 0 to n, you get 0 minus 1 factorial, which is not defined here. So right, and you know that this sum anyway is 0 for k equal to 0, the contribution. So you can manipulate it, and because I have to go a little fast here, I do not want to spend too much time on all these manipulations, right, and this manipulation gives you the answer NP. It is very easy to manipulate. All you have to do is write this as p power k minus 1 into p and take that p out, and you will get and this has n into n minus 1 factorial, and the n and the p will come out and the rest of the sum will add up to 1. So verbally I will dispose of it. Right. The e of x squared is more elaborate, right? It is not so simple, but it's just a couple of more steps. You put k squared here instead of k, right, and you can still do the same type of simplification, and what you get is, let me make sure I don't mess up here, it is it's n squared n squared p squared plus n into np into n minus p. This is what you should get. It's if you just do it directly, it is a bit of a mess. It is not as simple, but I've worked it out here. But I if I keep writing all that down, it becomes too much time is taken up. So you have an n squared p squared here. Let me write it very clearly. It's n squared p squared plus, and anyway all these results are available in lots of places. So I don't think we should worry too much about exact formulas, right? Okay. So then I just want to summarize them here, because these are things that we will be drawing on a lot. So please commit some of these to memory so that when it's needed you can pull it out. What about Poisson? If you do Poisson lambda, you can show that E of x is exactly lambda. Again, this is not too difficult. This follows exactly the summation here, because k times there is a k factorial here. Okay, maybe I should maybe I'll do it here. I don't want to. So for the Poisson case, I get E of x as sigma k equal to 0 to infinity, right? What are the product terms here? We'll write it out fully so that we don't mistake anything or miss anything. So k into e power minus lambda to the power k divided by k factorial, and all you have to do is cancel. So this becomes k equal to 1 to infinity e power minus lambda power k minus 1 into lambda divided by k minus 1 factorial. I have to deliberately write it like that, and then I will put k prime equal to k minus 1 or something, and you will find that this lambda will just peacefully come out here, the rest of it will add up to 1, exactly like the binomial. Similarly, you can show that E of x squared for the Poisson case is lambda squared plus lambda. So E of x is lambda and E of x squared is lambda squared plus lambda. Manipulations of this kind I am going to leave it to you, because it's a total waste of time for me to do it on the board. I hope that you people will have no difficulty in these types of manipulations, right? Because this is not the kind of thing that we are to be spending time on here. If you have any difficulty, please contact me offline. I can guide you. It's really not. All you have to do is put k squared here, for example, and then do the same kinds of manipulations on that. I've done it here, in fact, and it's not very complicated at all. It comes in 3 or 4 steps. Okay. What about the continuous case? For the continuous case and also for the discrete case, we have a very important result regarding the E of x, or the mean. Remember, what did I say yesterday? E of x is also called the mean of x. You also write it as mx with all these subscripts are all with uppercase, right? You are referring to the random variable, and so it has to be uppercase. The important result regarding the mean is that, especially for a continuous PDF, the continuous case is that if there is a point of symmetry in the PDF and if the mean exists, then that point of symmetry must be the mean. So mean equals point of symmetry. Actually it's true also of the PMF case, but PMFs are typically not particularly known to be symmetric, except the case of half-half, Bernoulli half-half, right. Bernoulli half-half you can sort of say is probability half is sort of symmetric about the value half in the middle, 0 and 1 are but that is a very special case. So we won't think of, generally we don't view PMFs as being symmetric, but PDFs definitely. So if the mean exists, of course, right, in the Cauchy case mean does not exist, so even though there is a point of symmetry, it is not regarded as a mean. So, but most importantly in the Gaussian case, if I pick the arbitrary Gaussian PDF with mean parameter m, now we can call it the mean. So this PDF symmetric about x, right, about m, the value m. What do I mean by symmetric? Is it clear what I mean by symmetric? Means that if you take that is f of, that is i.e. I can write mathematically what is the symmetry condition, fx of m plus x will be equal to fx of m minus x, actually for all small x. That is the meaning of symmetry. Even if the PDF is limited, it is not of infinite extent, you still have 0 equal to 0. So if I have, for example, a uniform PDF from A to B, what is the point of symmetry of the uniform PDF? What is the point of symmetry of the uniform PDF? A plus B by 2, exactly. Why is there so much hesitation? So this implies that if x is u a b, will mean mx is a plus b by 2. Again, to prove this, okay, what I meant, I guess I am getting ahead of myself in some sense, that if this is true, if there is a point of symmetry, then okay, I have written it here, the mean must be that point of symmetry. So for the Gaussian case, there are two examples I have written, one is a Gaussian, the other is uniform. So that actually, right, belongs to this. So for the Gaussian PDF, the mean is, and how do I know the mean exists for the Gaussian PDF? It exists clearly because e power minus x square is such a strongly decaying function that it turns out you can do x power any integer and the expected value of that quantity will still be finite. E of x power k will exist for any k for the Gaussian case, unlike other PDFs which are fall off as some polynomial function like 1 by x squared, for example, even mean does not exist. If you take 1 by x cubed, then mean will exist, but the square e of x squared will not exist. But e power minus x squared is strong enough that, and e power minus x itself, even the exponential PDF itself, right, is, even though it does not have a point of symmetry, it's still the decay is strong enough that every e of x power k will exist. So it turns out that is a simple factorial function. You can but anyway, at least or I should say the gamma function in general. Okay, so for the Gaussian case, without doing any integration, I know that the answer has to be m. So again, there is a lack of time here, so which means I have to, I cannot spend more time on this than I want to, but I think you people are mature enough now to go and think about it yourself and derive, maybe even derive this result. All you have to do is you split that integral into two parts and make this substitution in the two parts am I talking about, up to m and above m, and you make this substitution, you can easily derive this. The mean has to be the point of symmetry. of course you satisfy yourselves before doing any computation that the mean actually exists, which is for most PDFs mean will exist, right. Only the Gaussian is a very rare case, right. For example, exponential itself. So and among the discrete examples I forgot to include the geometric. So one thing again a takeaway from this whole course is that the exponential and geometric are very highly similar, right. They are all almost counterparts of each other, right. You have the exponential in continuous space and geometric in discrete space, but otherwise they are very lots of very similar properties, especially the memoryless property that we talked about, right. So here what happens is you have E of x as integral 0 to infinity. One example we will do just to show how this integral works out. So I hope no right this is doesn't need any further explanation. Where is this x coming from? It's because I am calculating the E of x. If I wanted E of x squared, what would I put here? I would put x squared. How do you go about if you are in 12th standard and somebody gave this to you, what would you do? You would integrate by parts. So the same thing you have to do here. Remember I said in the beginning of the course you can't run away from integration if you want to do this business. So you have to brush up on integration by parts. I don't know if you've already seen it in this course, but we're seeing it here, right. So what happens to this? I mean, again I don't want to write out all the steps, that's for the 12th standard student and not to be done here. So finally you get the answer. What answer do you get? You get you get 1 by lambda. One divided by lambda. It should not be too much of work for anybody, right. So why is this reciprocal dependence on lambda? And similarly E of x squared, let me see if I've written it down correctly. I don't want to right I don't want to so okay, E of x squared is not is again two terms, not one term. It's actually 1 by lambda whole squared. No, it's 2 by lambda squared. Again integrate by parts or use the gamma function definition. What is the gamma function definition? Is something very similar to this, right. You look up the gamma function. So this is basically if you take a k here, it will be k factorial divided by lambda power k or some such thing, but we are not going to go anywhere beyond 2 definitely in this course, right. So these are the most important two things that we care about. So why is this inverse relationship with lambda coming? That is the intuition I want to bring out here. Remember the spread of that PDF. How does the PDF behave for large lambda and for small lambda? For large lambda it spreads out. No, sorry, for large lambda it's tall and skinny, right. Probability is concentrated around 0. Remember this is the PDF. So lambda is inversely proportional to the spread of the PDF, okay, as far as exponential is concerned. Unfortunately we write it as exp of lambda only, not as 1 by lambda, right. So you have to remember this, for the exponential PDF lambda is inversely proportional to the spread. The larger the lambda, the smaller the spread, and more closer it is to 0. All the probabilities are sitting close to 0. So the mean also will be smaller, will be small if lambda is large, and similarly this E of x squared. On the other hand, if the smaller you make lambda, both the mean and the mean squared value will get pushed out. So so if you have this versus this, right. So this will clearly have larger mean. compared to this. Not just mean, also larger mean squared value and relatedly and by extension the variance, which we have not yet defined, but we are going to do so in a very short while, isn't it? So this parameter lambda is very important to the exponential PDF. It controls everything about the exponential PDF. Unlike the Gaussian, which has two parameters, this m and sigma squared have two different roles to play, right? M only tells you the location of that PDF along the x-axis. Sigma squared controls the spread, but here this lambda does everything. Okay. Now I forgot to add in the discrete domain, we also have the most important I shouldn't say very important geometric PDF, right, which is the counterpart of this. So when I do so let's say I do x is geometric P. What do you think the mean value is here? How do I go about finding the mean value for this? Again, I have to do a summation. So k times 1 minus p to the power of k minus 1 into p. What values of k? K equal to 1 to infinity, because I am assuming that this is my definition of geometric PDF. It goes from 1 to infinity, and the PMF is 1 minus p whole power k minus 1 into p. So this is the PMF, and this value of x multiply and sum. How do I know it exists? Because again it is an exponential fall off. What kind of sum is this? AGP, and it turns out that the way to sum this, it turns out is to, one simple way to do it is to differentiate some identity. You do not have to remember the formula for this crazy AGP, because the AGP formula actually will work for any finite sum also, but we are not doing a finite sum here, we are doing an infinite sum. So for the infinite sum you do not have to remember any formulas. Instead you can take the geometric identity and differentiate with respect to p. What do I mean by that? What is the geometric identity here? The sum identity, right? The sum identity is simply, if I go and if I look here, that is for the geometric, if I write the identity as, I will write it as sigma, okay, I will write the full identity here, 1 minus k times p, k equal to 1 to infinity is 1, isn't it? This is the basic property of the geometric PDF, PMF itself. Now I will take this p and divide by p here, just to make it easier. This is also correct, because p is non-zero. I can divide by p. Now I want to differentiate both sides of this with respect to p. Why? And take the d by dp inside the summation. How am I justified in doing that? I am justified in doing that because the sum is absolutely convergent. That is, this is actually a sum of positive quantities, there is no plus minus terms here. So I can take d by dp on both sides with p and take the d by dp inside the summation. Doing that gives me this. What do I get by, and that too I may have to do some modification of this. It is probably better to write this as k prime equal to 0 to infinity and so on, right, so that I do not like this k minus 1, but anyway this is minus 1 by p square. So you can, what do I get out of this manipulation? I get basically that k term coming here. Can you do it and see? You should be able to get this, the answer. What is the answer? What is this? What does this evaluate to? It has to evaluate to 1 by p, right? Can you complete the rest of the exercise? Just write this instead of 1 to infinity, think of it, rewrite it in a small minor change from 0 to infinity instead. So which is actually just nothing but 1 minus p power k 0 to infinity is still 1 by p, is it not? And that is and then so you don't have to worry about this k minus 1 and all that, right. So this basically equals, this will equal from here, this equals the important result 1 by p. So you notice that this p and this lambda are sort of play the same roles. The smaller the p, the bigger the mean. Why is that the case? Smaller the p means you have generally more number of trials till you hit the first success, which means the average number of successes is going to average number of trials till the first success will increase. So the inverse relationship with p. Similarly, this e of x squared, it turns out this is e of x. E of x squared can also be done with k squared here. You can do one more differentiation of, you write the identity again, differentiate once again with respect to p, and then you can get this answer 2 minus p by p squared. So like you have a lambda squared here, you have a p squared here. So the smaller the p, both the mean will grow as 1 by p and the mean square grows as 1 by p squared. Okay, so the exponential and geometric are highly, right, very highly interlinked in more ways than is obvious. So but right, but and they have mathematically these kinds of things, right, prove their similarity.